Okay, welcome back everybody. So in this last and final lecture, the final part of my course, we are going to finally go back to the fractional ideals, and as I promised in the beginning, we are going to classify the isomorphism classes of certain abelian varieties over a finite field of Q in terms of the ideal classes. So this classification is going to be of functorial nature, so we're going to define the equivalence of categories. And in order to do so, I need to introduce some notation first. So for today, let Q be a power of a prime number P, and we are going to write P to the power D, it as a P to the power D for P a prime. And we are going to denote by AVQ the category of abelian varieties over the finite field of Q. So this is the category whose objects are the abelian varieties over Fq, and the maps are the homomorphisms of these abelian varieties. Okay, cool. Recall from what we have seen in the last video that to each abelian variety, abelian variety A in such category, we can associate a monic polynomial. We can attach to it a monic polynomial h of A with integer coefficients, so in the polynomial ring Z with the variable x, of degree twice the dimension. So 2 times the dimension of A, which identifies A uniquely up to isogeny. Okay, and remember that explicitly we have seen that this h of A is the characteristic polynomial of the Frobenius endomorphism acting on L dictate module of A for any prime L different from the characteristic. Okay, so this was the definition that we have seen the last time. Excellent. So now we are going to focus on a subcategory of this AVQ. So namely, we are going to look only to the abelian. We are going to only look at the abelian varieties that are called ordinary. So A in AVQ, so an abelian variety over FQ is called ordinary. If one of the following equivalent condition holds. So 1. The P rank of the abelian variety is maximal. So remember that the P rank was the size of the P torsion of the abelian variety. So you take the points over the algebraic closure of the field of definition that are killed by P, the multiplication by P. So we know that this is going to be a group Z modulo PZ. So a bunch of copies of Z modulo PZ, and there exists an integer here that I'm going to call F, so that makes this an isomorphism, and this F is called the P rank sorry, I want to say that the P rank has to be G, the dimension of A. So ordinary means that the P rank here is maximal. So it's equal to the dimension. So in characteristic P, one of the phenomena that can happen is that this number varies between 0 and G. An abelian variety is ordinary if and only if this is equal to G, equal to the dimension of the abelian variety. 2. The second equivalent condition is that half of the roots of the characteristic polynomial over the p-adic numbers, so in QP bar, are units, are p-adic units. And the third equivalent condition is that the coefficient of h of A of the polynomial, of the characteristic polynomial, the coefficient of the variable x to the power g plus 1. So when you write the polynomial, this is a polynomial of degree 2g, so you look at the coefficient in front of x to the power g plus 1, and we want it to be coprime with p. So this is an integer, right? The characteristic polynomial is an integral polynomial. It's a polynomial with integer coefficients. And we want this integer to be coprime with p, where p is the characteristic of the field. Okay? Right, let me give you an example about this ordinary condition. So we look at elliptic curves. So what happens for elliptic curves? So let A now be an abelian variety of dimension 1, that is an elliptic curve. Over Fq, over a finite field Fq. Then the characteristic polynomial is a polynomial of degree twice the dimension, so in this case it's a quadratic polynomial. So we can write h of A as x to the power 2 minus some coefficient Tpx plus q. This will always have this form. Think about it a little bit. And Tp is going to be the trace of the Frobenius. Right, remember this is a characteristic polynomial. So q is going to be the norm and Tp is going to be the trace of the Frobenius. Okay, and there is this theorem by Hasse and Weil that tells us that the absolute value of the trace is strictly smaller than 2 times square root of q. And in particular, if Tp is coprime to P, so if the greatest common divisor of the two is equal to 1, then A is ordinary. Otherwise, so if P divides Tp, then we say that A is supersingular. So we have only these two possibilities in dimension 1. In general, in higher dimension, there are some intermediate classes that are, to some extent, are parameterized by this P rank that I just mentioned before. In any way, we are going to focus on the abelian varieties that are called ordinary. So as the name suggests, this ordinarity is, well, it's a very common condition. Most abelian varieties are going to be ordinary. And one way to think about it, even if it is not really a proof, is mainly like a kind of intuition, is that this being coprime with P is an open condition, it's a Zariski open condition. So P divides an integer if this integer is congruent to 0. So in terms of Zariski topology, this is a closed condition, while being coprime means to be non-zero modulo P, so it's an open condition. More precisely, this statement can be made in terms of the moduli space of the abelian varieties, with some extra structure, like, I don't know, principally polarized abelian varieties. And the locus of ordinary abelian varieties is the biggest one. It describes most of the abelian varieties. But I'm not going to go dig into that because the theory of moduli spaces is complicated and will require like 1 or maybe 2 more courses of its own. In any case, what I want now is to define a new category, namely the subcategory of AVQ that consists only of ordinary abelian varieties. And then we are going to try to understand this category in terms of algebraic terms. All right. Definition. So we write A, V, Q, and ord for ordinary, and this is going to be the full subcategory of AVQ, consisting of ordinary abelian varieties over FQ. Okay, so full, if you are not familiar with category theory, simply means that given to ordinary abelian variety, we look at, and if you look at the Hom set, we take all the Hom set. So we don't exclude any homomorphism between the two of them. The Hom set in this subcategory are the same as the one in AVQ. But the objects, we consider only the objects that are ordinary. Okay, so this is the first category that I wanted to define. And now I'm going to define another category, which is going to look quite different. I'm going to denote it by M ord Q. So Q again for ordinary, ord again for ordinary, Q for the finite field that we work with. And now I'm going to say that M stays for modules. Indeed, so this category will have objects that are pairs T, F, where T is a free finitely generated Z module finitely generated abelian group, so Z module is the same, and F is a Z-linear map, so a map of abelian groups. So it's a Z-linear endomorphism actually. So it goes from T to T. That satisfies the following condition. So such that 1. Its extension, when you extend the coefficient to the rational, is a semi-simple map. And its eigenvalues, so the root of the characteristic polynomials, have complex absolute value square root of Q. right? So observe. The characteristic polynomial of this map is an integer polynomial because this is a map between three z modules of finite rank. And we are requiring the eigenvalues, so the roots, to have absolute value square root of q. So in other words, the roots are q-Weyl numbers. 2, so second condition that this f must satisfy is that half of the roots of the characteristic polynomial so the characteristic polynomial of f tensor q over qp bar, so over the algebraic closure of the p-adic numbers, are p-adic units. Right? So this is going to be the ordinarity condition. So as if you've seen, as I've seen before, one of the equivalent definition of being ordinary is that half of the roots of the characteristic polynomial are p-adic units, and this is exactly what we're going to ask here. And 3, there exists another z-linear morphism, V, that goes from T to T again, such that f times V is equal to V times F, so the composition of the two in both sides is equal to multiplication by Q. So multiplication by Q, I mean Q times the identity map, of course. All right. Great. So these are the objects in this category MQ ord. So you might wonder what are the homomorphisms in this category. So let me just write it down. So in M ord Q are commutative diagrams that look like that. So you take, so more precisely, they are z-linear maps between two pairs, I don't know, T to T prime, but they have to be compatible with these endomorphisms F. So you want something, a commutative square like this. Right? So you have a pair TF and you have another pair T prime F prime, and a map from TF to TF prime is a z-linear morphism from T to T prime that commutes with the action of these Fs. Okay? And of course we want phi to be z-linear. So a map of abelian groups. Okay, and now the big theorem. Theorem. This is a theorem by Deligne. It's one of his Invenciones paper. The paper is something like 5 or 6 pages, but it's fantastic. So there is an equivalence of categories which I'm going to denote by F ord, so induced by a functor F ord that goes from A, V ord Q to M the category of modules, M or Q. And this equivalence satisfies the following properties. So if, so right, let's say that an abelian variety is, an ordinary abelian variety sends to the pair T A, f of A. So then the rank of this T of A as a Z module is equal to twice the dimension of A, and as maybe the notation suggests, f of A is going to be the image of the Frobenius endomorphism of A, of pi of A. And similarly, V of A, which is the map that goes in the both direction in the definition of an element here, is the image of the Verschiebung of A. Okay. So I'm not going to give a detailed proof of this theorem because it requires techniques that are quite advanced, but I want to give quite a sketch of it. So I want to tell you precisely what this functor f ord is. Okay. So what is f ord, this functor? So take an abelian variety which is ordinary, so over fq. Now, denote by W the ring of Witt vectors over fq. The Witt vectors of fq and fix an embedding of W inside C. So if you haven't seen Witt vectors in the past, you can think of them as p-adic numbers. This is not very precise, but this is actually true if q is equal to p. So if q is actually a prime, not just a prime power, then they are just the p-adic numbers, the p-adic integers. And there exists well, as a consequence, or there exists an embedding. One can prove that there exists an embedding from the algebraic closure of the p-adic numbers inside C. So this embedding exists as a consequence of the axiom of choice. So it's very, very abstract. It's not something that we can really put our hands on. Nevertheless, this is very important for what we are going to say later. And I'm going to also denote it, give it a name, and denote it by epsilon. And I'm going to use this epsilon throughout to denote it. Okay? So another big black box that we are going to use is that ordinary abelian varieties are distinguished among the other abelian varieties over fq because as they are the one that admit a canonical lifting. So A is ordinary, and this implies, as a consequence of a theorem by Seren-Tate, maybe, or Grothendieck-Messing theory, as you prefer. There are various references with slightly different proofs. In any case, what they say, or what we can deduce from this theorem, is that there exists an abelian variety A tilde over W, over the Witt vectors, that is a lift of A, which means that it reduces to A once that you look at the residue field. You reduce it modulo P. So there is this lift A tilde satisfying an extra condition, a very strong extra condition, namely that all endomorphisms lift. So the endomorphism ring of the abelian variety over Fq is equal to the endomorphism of A tilde over the Witt vectors. So this is a very strong condition, and nevertheless all ordinary abelian varieties is satisfied. And this is actually a characterization of this special lift, and it's called the canonical lift, or canonical lifting. Yeah, and it is very cool because this means that these ordinary abelian varieties can be lifted from positive characteristic to the Witt vectors, which is a ring living in characteristic 0. It's something that can be embedded in C, right? So we are getting close to a complex abelian variety. That is something that, as you have seen in Anna's course, we can really put our hands on. All right, but let's finish defining this F-ord. So we have this canonical lifting, and we have an embedding of the Witt vectors inside the complex numbers. And now we can construct a complex abelian variety. So put AC to be the base extension of the canonical lifting to the complex numbers. So we take the fibered product along the embedding that we have fixed to the complex numbers. And finally, we can define T of A, the free finitely generated Z module of the pair, as the first integral homology of this complex abelian variety. Right? So remember that when you have a complex abelian variety, you can construct the analytic representation. So it's a complex torus. You can look at it as a complex torus. So a complex vector space of dimension G, the dimension, divided by a lattice. And this lattice is isomorphic, can be thought of as the integral homology, the first integral homology of the abelian variety. And then we still need to define what is f of A, so the second element of the pair, this endomorphism that, as you can expect, is going to be the Frobenius. And why it's the Frobenius? Because every step in this construction that you have seen is functorial. So taking the canonical lift is functorial. So we get so even if the canonical lift lives in characteristic 0, there exists a map that it acts as a Frobenius, in the sense that when you reduce it back, you get precisely the Frobenius. This is quite a magical thing. So you are living in characteristic 0, but there is a map that reduces to the Frobenius. It's quite something. And moreover, also taking the base extension to C is functorial, of course. It's just like a base extension. And this means that we get an induced Frobenius on this AC, and also taking homology is functorial. I almost forgot that. And in particular, we get that there exists an endomorphism f of A acting on T of A. That represents the Frobenius. The Frobenius pi of A of A. Cool. So we have defined T of A and F of A, and of course now we put F ord of A to be precisely the pair T of A, comma F of A. Okay, so this is the functor that induces the Deligne equivalence. So So we have seen the classification up to isogeny of the abelian varieties. There is this correspondence between this characteristic polynomial, so a very algebraic object, and the isogeny classes. And now we have done also the first step towards a classification up to isomorphism in certain cases. We have seen that there is this theorem by Deligne that expresses the abelian varieties over finite fields, the ordinary ones, into some modules, these free finitely generated modules with these Frobenius, this endomorphism that acts as a Frobenius. Great. Now we go even further and we focus on the case when the characteristic polynomial is square free. So. All right, let me be very precise about what we need. So now let H be an ordinary square free characteristic polynomial of some abelian variety. So some abelian variety over Fq. So in other words, we have that, let me just rewrite it in a slightly different way. We have that H is equal to H of A, so the characteristic polynomial of the Frobenius of the abelian variety A, for some A in the category AV ord Q. So ordinary abelian varieties over Fq. And we require this polynomial to be square free. So square free means that that H, so H is H of A is square free. So it factors into polynomials, distinctly reducible polynomials, H1 times H2 times H of R. So each Hi is irreducible, and these are pairwise distinct. Okay. And observe that this factorization respects the Poincare decomposition of the abelian variety A. Indeed, if A is isogenous to B1 times BR with BI, each BI simple and pairwise non-isogenous, then the factorization into irreducible of the characteristic polynomial respects this factorization here. In other words, you have that Hi, after possibly changing the indexes, of course, you have that Hi is equal to H of Bi. Okay? And let me stress one thing that maybe to avoid any confusion, and I will write it even as a remark. Here we are using the non-trivial fact that in the ordinary case, so for an abelian variety B in AV ord Fq, every ord Q, the characteristic polynomial is irreducible if and only if the abelian variety is simple. Okay, so in the last lecture, in the last video, I told you that for a simple abelian variety, the characteristic polynomial is a pure power. It's the power of an irreducible polynomial, the minimal polynomial of the Frobenius. So the characteristic polynomial is a power, but these two, the minimal and the characteristic, might not coincide a priori. There is this exponent that had that formula that we could explicitly compute, but there was no guarantee that the exponent will be 1. In the ordinary case, we have it. So irreducible characteristic polynomial if and only if the abelian variety is simple. So which means that HB, if B is simple, is not just the characteristic but also the minimal polynomial of the Frobenius. Okay. All right. Now that we understand in which case we are working, let me define some other two subcategories of AV ord and M ord Q. All right. So definition. We consider, so define or denote by, let's write it like this, denote by AVH the full subcategory of AV ord Q consisting of abelian varieties A, ordinary over FQ, such that the characteristic polynomial is precisely this H that we fix. Okay, so we take H square free, ordinary over FQ, and this will correspond to a characteristic polynomial of abelian variety, and we consider the category consisting only of those. So in other words, these are precisely the abelian varieties isogenous to this fixed A, right? By Ondas theory. By Ondas theory, isogeny class, characteristic polynomial. So if we fix the characteristic polynomial, we are fixing one isogeny class. So this is isogeny class of A, right? Cool. And now we define the corresponding category in terms of the Lie modules, in the world of the Lie modules. So definition again, denote by MH, modules with characteristic polynomial H, the full subcategory of M ord Q consisting of pairs T, F, where the characteristic polynomial of F is precisely H. Okay? So remember, F is an endomorphism acting on this free finite regenerated module. So after choosing a basis, you can think of it as a matrix with integer coefficients. You can compute the characteristic polynomial of this matrix, and we wanted it to be H, precisely H. So the characteristic polynomial of this matrix is H. And remember that this doesn't depend on the basis because it's a characteristic polynomial. If you change the fixed basis, so in other words, you represent F as a conjugate matrix, you will still end up with the same characteristic polynomial. So this definition is well posed. Great. So now let me rephrase the theorem of the Lie with this new extra notation that we just introduced. Corollary, I'll write it as corollary. The functor F ord that we discussed not long ago induces an equivalence of categories between AVH and MH. Okay? And the reason is that, as we have seen, by construction, F ORD was sending the Frobenius endomorphism of an abelian variety on the left-hand side into the F endomorphism. So in particular, the characteristic polynomial of the Frobenius here, with the term which determines the isogeny class, is going to be the same as the characteristic polynomial of the matrix F, of the endomorphism F. Great. And now let me introduce some notation and try to understand better this MH. And maybe you have already realized it, that we actually know already a lot about this MH. The only thing that we need to do is to twist our perspective a little bit, change it. And now I'm going to be very precise with what I just said and explain you what we actually are looking at. So let me first introduce some notation. So put R to be the polynomial ring in two variables with integer coefficients, x and y, divided by the ideal generated by the polynomial h, so the characteristic polynomial we are looking at, and we think of it in the variable x, and the polynomial xy minus q. Okay? Observe that R is an order in the étale Q algebra defined by H, which I'm going to denote by K. So Q, X, polynomials with integer, rational coefficients modulo the ideal generated by H of X. Okay? So remember from the beginning of the part 1 of the course, we know that an order is a subring of this algebra of maximal rank as an abelian group. And also, let me stress that this is a Q algebra because H is square free. So H is a product of distinctly irreducible polynomials. So this K here is a product of a number field, product of number fields. In particular, this is equal to Qx product of Qx modulo Hi, where Hi are the irreducible factors. Okay, we are not going to use it, but just to fix the notation even more. Okay, so this R is an order inside here. Cool. And I'm just going to remind you of the notation that we introduced in part 1. So denote by I of R the category of fractional R ideals. Okay, so the object of this category are the fractional R ideals of this order R, and the maps are R linear morphisms. All right, and now let me restate again the corollary that I just wrote over there, using fractional ideals now. Theorem. Oops. So there is an equivalence of categories between M of H, so Deligne modules with characteristic polynomial H, and the category of fractional R ideals. Okay, so let me give the proof. The proof is very easy. It's just a matter of staring at these two categories for a little longer, for a while, but let me just be very precise. So take a pair on the left-hand side. So for each TF in MH, we have a canonical isomorphism between the ring ZFV and R. Okay, so this is the ring where we add the endomorphism F, and we add also the endomorphism V, which by definition was just Q over F. So if you remember, in the category of Deligne modules, we require the existence of this F, which is the Frobenius-like, and among the various parts of the definition, we also needed like this F to have a almost inverse. So we needed a V such that F times V is equal to Q, and V times F is also multiplication by Q. So in other words, we have these two marked endomorphisms. And now we created a ring generated by these two, and I'm claiming here that this is isomorphic to the ring, to the order R that we just defined. Okay, and the isomorphism is the obvious one. So you take F and you send it to X, and you take V and you send it to Y. Okay, so it's nothing fancy. By the very definition of R, we are modding out by the characteristic polynomial H, which is assumed to be irreducible, square-free. So in particular, it's equal to the minimal polynomial of F. And then we also mod out by the relation xy minus q, which tells us precisely that the multiplication of the two variables is going to be equal to q in the quotient. Great. So we have this isomorphism. Let me continue the proof here. And now, since T, by definition, is a free finitely generated Z module with this F acting on it, and also with this V acting on it, so it's a ZFV module. Oops. So it's a ZFV module of maximal rank. So the rank is equal to the degree of the polynomial H, which is also equal to the dimension, by definition, of the algebra K over Q, when you look at it as a vector space over Q. So in particular, we can canonically identify, so T can be identified with a fractional ideal of R, right? A fractional ideal of R is precisely an R module of maximal rank inside K. So it's really the same thing as this T, morally. And let's be explicit also about the converse association. So this allows you to go from the modules to the fractional ideals, and now let's go back. And it's even more clear. So if you take a fractional R ideal, by definition, I is a free Z module of rank equal to the degree of H. So you just take t, so in the association in this direction, you just take t to be equal to I. And the map F is going to be just the action of the variable x on it, right? So there is nothing else to add. So it is an element of MH. And this concludes the proof. Okay, so let me say a few words about what we just did, because it might sound like, okay, we haven't proven anything, we just restated things, the definitions. But, okay, so this category MH that we just defined can be thought as modules with two marked endomorphisms. So this F and this V, and V can be reconstructed directly from F. So the only important one is actually F. So as I said, F is a matrix. Right? Once that you choose a basis, you are actually working with a matrix F. And when you instead look at the fractional ideals, you're shifting this perspective. Instead of staring at the map F, at the matrices F, you kind of fix them. So these are all going to be like the variable x modulo these polynomials. And instead, you look at the basis on which it can act. And these are precisely the fractional ideal. So what we just did is just shifting the perspective, going from the abstract context of the Lie modules into the embedded context of fractional ideal, embedded inside a fixed étal algebra K. So, yeah. So nothing very exotic. It's simply just like looking at the things from another perspective. So let me sum up what we just did in the last few theorems and corollaries. So to sum up, we produced a bunch of equivalence of categories. So we have something that goes from abelian varieties in the isogeny class determined by H. We have n length into MH. So this was the Deligne functor F ord. And then we have these other equivalence of categories that I just defined that lends into the fractional R ideals. Okay? And I'm going to denote the composition of this functor, which is also an equivalence of categories, because it's a composition of two equivalence of categories, by G. Fancy G. Okay? Cool. So we have an equivalence of categories between abelian varieties over finite field with characteristic polynomial H, so some very exotic, complicated to understand object into fractional ideal. Something that we can really put our hands on. We have Z bases, we can understand, we can multiply, intersect, everything can be done explicitly, either by hand with some work or on a computer in a fraction of a second. And let's deduce, so we understand this category a lot better. We can immediately understand a lot of things about the corresponding abelian variety. So let me just write this as a corollary. What we get immediately from just the definition of this functor. So corollary, let me just move the G above the arrow so I have a little bit more space. G. So corollary, let A be an abelian variety in the source category. And put I to be the image via this functor of the abelian variety. So G of A. So this is a fractional R ideal. Okay? Then, so 1, the endomorphism ring of the abelian variety A equals the multiplicator ring of the fractional ideal I. Okay, so this is an over order of R. Remember? 2, the automorphism group of the abelian variety A equals the unit group of this multiplicator ring. So all the elements that are invertible. And 3, I need more space, so let me erase this board. So 3, we have that if A is isomorphic to a product B1, BR. So remember that we know about the isogeny decomposition, but here we are saying if A is isomorphic to this to a product, so this happens if and only if the fractional ideal is equal to a direct sum of fractional ideals inside K. And this happens only if the endomorphism ring of I is also a direct sum. Okay, and step 4. So what about the isomorphism classes? Well, this is an equivalence of categories. So we have that the isomorphism classes of abelian varieties in the isogeny class H is in bijection with the ideal class monoid of R. Okay, so the monoid of ideal classes, of isomorphism classes of fractional ideals. And so the motto is that we have seen in part 1 how to compute this guy. So we can compute this guy as well. We can compute the left-hand side as well. Cool, right? So, yeah. And let me say a few more words, just en passant, since we are on the topic, about the abelian varieties. Right, so we know that abelian varieties are in general projective, right? So they can be expressed in terms of equation living inside some projective space. As you have seen with Anna, or with Christoph, this in dimension 1, this is very nice and easy. We always have a canonical form of the equation. We know how the equation looks like. So we have 2 variables, 2 coefficients, sometimes more if you are in small characteristic, if characteristic 2 or 3. But in general, we have a closed form. Unfortunately, this is a lot more complicated already in dimension 2. So it can happen, actually, the general form of an abelian surface requires 16 variables and it's something like 72 equations. So it's already a lot harder to handle. You cannot express them with, I don't know, 1 or 2 equations. They are not a complete intersection, so it's really messy to work with them. And using fractional ideal, on the other hand, is a much more efficient way to represent them. In dimension 2, I invite you to think about how do you write a fractional ideal corresponding to an abelian variety of dimension 2. So you need 4 generators, the z-basis, so this is a lattice in an étal algebra of dimension 4 over Q. So you need only 4 elements of the étal algebra to express it, which is much better than 72 equations in 16 variables, if you think a second. Cool. All right? So we understand the isomorphism classes of these abelian varieties. We can compute them. We can compute endomorphism ring, automorphism groups. And now let's see if we can compute something more, namely polarizations. So you have seen during the course of the lecture, so in this school, the polarizations are a very interesting object and important in a, let's say, intrinsic way in terms of for the abelian variety. In some sense, they encode the way this abelian variety embeds into a projective space. So they are very important. So let's see, can we understand polarizations also in terms of this fractional ideal? Well, the answer is yes. And let me define things and tell you how this works. So consider a polarization of some abelian variety A in our AVH. So we are going to represent polarizations as isogenies between an abelian variety A and its dual. And so this arrow lives in the category AVH. So again, H is as before, so square-free, ordinary, Q-Weyl polynomial. And now the question we want to answer is, what is G the functor that we just defined of this diagram, of this lambda. All right, so yes, so we have defined the Q et al. Algebra K, and from the CM theory that you have seen before, you know that this Q algebra comes with an involution. So this is what we call a CM algebra. So K, which is, remember, the Q et al. Algebra defined by the polynomial H, is a CM algebra, which means that there exists an involution which actually we can write explicitly. This is the map that sends F into F bar, so we denote this involution with a bar, and F bar is precisely V. So once that you know this, you know how it acts on the wall algebra. Yeah, now I'm going to identify K with QF to simplify a little bit the notation, and also the order ZFV. I'm just going to write equal to R instead of isomorphic. So we know that they are isomorphic, and in the isomorphism is the obvious one. So I'm just going to identify them. All right. Yes, so we have this involution on this algebra. F goes to F bar equal to V. And we know that this acts as complex multiplication after applying any embedding into C, or better, any homomorphism to C. Any map psi from K to C. So let me write it explicitly what we are saying. So you take, oh sorry, I wanted to call it phi. So phi of some element alpha bar is equal to phi of alpha with a bar on top. So this is the bar acting inside K, and this is the bar acting on the complex number. All right, and this is true for every alpha in K. All right. Okay, and observe that if the degree of H is 2G, so we know that the degree of the characteristic polynomial is twice the dimension of any abelian variety in the isogeny class, then the homomorphisms from K into C comes in pairs, G pairs of maps. So if deg the degree of H is equal to 2 times G, G the dimension of any abelian variety inside AVH, then the homs from K to C, this set can be written in pairs. So there is phi 1 and then phi 1 bar, phi 2 bar, and so on up to G. Okay? All right? And definition, as we have probably already seen with Anna, a CM type of the étale algebra K is a choice of a subset of this hom K to C, so of these 2G embeddings, where we take only one per pair. So we cannot take phi 1 and phi 1 bar, we can only take phi 1 or phi 1 bar. So a CM type is a subset running out of chalk here, of G homomorphisms so such that the size of this subset consists of half of the maps, and we take only one per conjugate pair. So only one morphism per conjugate pair. Okay, so in other words, the whole set of homomorphisms can be expressed as the disjoint union of this psi, of this CM type, and its complex conjugate. Hom K to C, so the whole set of maps is equal to this subset, CM type, disjoint union with a bar on top. Okay, so you take the maps, you take their conjugates, these two sets are disjoint, and they form the whole thing when you put them together. Alrighty. Okay, now let me recall one thing before we state the last theorem. Just to recall the notation that we have introduced not long ago. So recall that in constructing the functor G, or better in constructing F horde and hence G, we fixed an embedding of the Witt vectors of Fq into the complex numbers, right? So this was like this weird embedding that exists as a consequence of the axiom of choice. Nevertheless, now we're going to need to get a hand on it. And let me define one CM type that depends on this psi. So observe that this embedding induces a p-adic valuation on C. So this is a p-adic ring. There is a p-adic valuation, and on the image we can get a p-adic valuation as well, right? So this induces a p-adic valuation Vp depending on epsilon on the image, which is inside C. And now we define, or we fix capital phi to be the set of embeddings from K to C, sorry, homomorphisms from K to C, such that the p-adic valuation, this p-adic valuation depending on epsilon, of the image of the Frobenius is strictly positive. Okay? And remark / exercise. Since the isogeny class we are looking at is ordinary, this subset phi is a CM type. So in the exercise sheet you will find this remark, you will be asked to prove this remark, and it's not hard at all, it just follows directly from the definition of ordinary isogeny class. But I want you really to sit down and write it up. So in particular, this phi consists of exactly G maps from K to C, half of the whole set, and these are all non-conjugate pairs. They are all non-conjugate, pairwise non-conjugate, all the phi's inside big phi. Great. Right, now we have all the ingredients to state the last theorem that will allow us to understand what polarizations are. And for simplicity of exposition, we will focus on principal polarizations, that is, polarizations of degree 1. So polarizations that are not just isogenies, but actually isomorphisms between an abelian variety and its own dual. Okay. So theorem. So take A, an abelian variety in our isogeny class, ordinary square free. Define I to be the image by the functor G of this abelian variety A, so our fractional ideal. And also, let's just introduce the notation of, we give a name to the multiplicator ring of this ideal. So we call it S. Okay, then 1, the dual abelian variety is mapped by the functor G to the trace dual ideal of I with a bar on top of it. Okay, so this, remember from the definition, consists all the elements. Now we put a bar on top of it because we have it here. So all the elements in K such that the trace from K to Q, so the trace has a map of our vector spaces from K to Q of X times I is inside Z. Okay, pay attention, we are putting a bar on all these elements. So it's not just the trace dual, but the bar of it. Okay? 2, an isogeny mu from A to the dual corresponds to corresponding by a G to an element lambda in the Tal algebra. So in other words, we are putting G of mu equal to lambda. Okay, so we take an isogeny, we look at the element in the Tal algebra that corresponds to the isogeny, and observe that, remember that isogenies are precisely the elements that are invertible in the endomorphism in the Hom zero set. So we want this element is going to be a non-zero divisor. It's a unit up to multiplication by some integer. Okay, so this corresponds to an element like this that sends the ideal I inside the ideal I bar T, right? So this is a map from A to its dual. So this is a map from G of A to G of A dual. Okay? And so this mu, we have that mu so this isogeny is a polarization if and only if the following two conditions are satisfied by this element lambda. So first one is that we want lambda to be totally imaginary. Okay, so lambda bar must be equal to minus lambda. We call this condition being totally imaginary. Sorry, this is a parenthesis. Okay, and the second one will involve this CM type phi that we have just defined. So we want lambda to be phi positive. Which means that for every embedding, for every homomorphism in this CM type phi, we have that the imaginary part of the image of lambda is positive, is strictly positive. So okay, this makes sense. Observe that this element is totally imaginary, so it will be sent to a totally imaginary element inside the complex numbers. And we want the imaginary part to be positive. So it's on the y-axis, and we want it to be on the top of it, on the upper part. Moreover, still part of 2, we have the degree of mu is equal to the index of the image of the multiplication by lambda inside the codomain. So the size of the cokernel. All right? So in particular, you see that this mu will be a principal polarization if these two conditions are satisfied, and if mu is actually is an isomorphism between the two ideals. All right? And then okay, another statement, 3, two polarizations, which we assume now to be principal for simplicity of exposition, so two principal polarization on the same abelian variety. So we take a fractional ideal, which is the image of the abelian variety, and two polarizations lambda and lambda prime. Are isomorphic if and only if there exists if there exists a unit of S. So S is the endomorphism ring of our abelian variety, the colon ideal, and we want to see this unit such that lambda is equal to V times V bar lambda prime. Okay? In particular, if I admits one principal polarization, so if I is principally polarizable, admit at least one principal polarization, then the number of principal polarization up to isomorphism equals the size of the following quotient. So then the number of principal polarization up to isomorphism equals the size of the following quotient. So you take units U in S star such that U is totally real and totally positive, and then you mod out this set by V, the units of the form V bar. Again, units in S. All right? So what does in particular mean? So we are saying that if I is principally polarizable, then there are these many principal polarization. And observe that this set does not depend on I, it depends only on S, which is kind of a funny thing. It's a non-trivial thing. Okay, 4. So given a polarization for the abelian variety A, so I lambda, we have that the automorphism group of the polarized abelian variety, so when we consider automorphisms that are compatible with the polarization, corresponds to the torsion units of S. And this set equals precisely the units such that V bar is equal to 1. All right, so this quantity is typically important when you want to do point counts on the moduli space, because you always want to mod out, you want always to make the counts weighted by the size of the automorphism group. So, okay. Right, so now I'm going to give an idea of the proof. The proof is not hard once that you understand what a polarization is. So I'm going to focus mainly on that. And then part 3 and 4 will be left as an exercise, so just diagram chasing. So the idea builds on results by Everett Howe, published in a paper that came out of his PhD thesis. So the paper is from 1995. And let me say how it works. So let me just briefly recall what was the functor f ord. So we were taking our abelian varieties over the finite field fq, right? And we associate to it the canonical lifting, which lives over the bit vectors. Okay? Then we complexify. We build a complex abelian variety, which is the canonical lifting tensored with C, and we have here it's important that we use the embedding of Evict vectors inside C, this epsilon, this tricky guy. And then the last step was to take the integral homology of this abelian variety. So you look at it as a complex torus, you take the analytic representation, and then you look at the lattice, the integral homology. And of course, this is all functorial, we end up with a Frobenius. Right, there is an F. Okay, right. So the complex structure of this abelian variety, by the very definition, as you see, depends on this epsilon. Okay, so in particular, we can remember this thing. So epsilon plays an important role in defining this complex abelian variety. Moreover, if we write AC as a torus, so V over a lattice lambda, which is actually the integral homology, is isomorphic to the integral homology, then the dual of this complex abelian variety corresponds to the dual torus. So you take V star modulo lambda star, where V star is it's the dual of the vector space, so maps from V to C, and lambda is the same thing, Hom lambda to Z, the dual of the lattice. Okay, and if you want to see details, I invite you to read Everett's paper, Howe's paper. But the key point is that now we use a pairing that is called the Weil pairing, which I'm not going to define, but I'm just going to say it. And the point is that using this pairing, one can deduce that the functor f ord sends the Frobenius of the dual variety so the dual over Fq to the map that corresponds to precomposition with a Verschiebung acting on the Deligne module. So the Verschiebung of A acting on, well, the dual lattice, okay? And I wrote precomposition between parentheses because in our case we are focusing on abelian varieties with a square-free characteristic polynomial, which particularly implies that the endomorphism algebra is commutative. So composing or precomposing doesn't really make a difference. Okay, so now let's focus to the fractional ideal world. What does this translate into us? So yeah, what does this mean for us? Means us two things. So first, so in I of R, we have that if, as we assumed, the abelian variety is sent by G to I, to the fractional ideal I, then the dual of A will be the trace dual ideal of I. So we need to take the dual lattice, so hom lambda to Z, and in one of the exercises you are asked to prove that the trace dual is the canonically isomorphic to the dual lattice. So the trace dual is isomorphic to hom from I to Z. But we also need to put a bar on top of it because the Frobenius become the Verschiebung, and the Verschiebung is F bar, V equal to F bar. So we put a bar on top of it. Okay, so this proves us, so let me write explicitly, because F bar is equal to V and the trace dual of an ideal is canonically isomorphic to hom the Z linear homomorphisms from I to Z. Okay? So we are using these two parts. Alright, so this tells us what the dual is in the category of fractional ideal. Cool. And now let me tell you how do we get when an isogen is a polarization. So the argument is similar. A similar argument, let me write it like this. So if you want the detail, again, please read the paper by Howe. There is explained very carefully. So the similar argument tells us that a polarization which on the complex sides is a map between the complex torus corresponding to the complexification of the canonical lift of A and lands into the dual torus. So we can see it as a matrix acting on these lattices, on this tori and hence on the lattices, and it has to be antisymmetric. Which in our category, by what we said, translates into asking lambda equal to minus lambda bar. and it must be positive definite. This is more or less the definition which you have seen with Anna in her complex treatment of the polarizations. There's maps between complex tori. And this must be positive definite, but with respect to the right complex structure. And remember that the complex structure was dependent on the epsilon. Because we are still coming from characteristic P, so this epsilon is really part of the data. And if one rolls out all the definition that we had given, this means that lambda must be phi positive for the CM type that we defined using epsilon. Okay. Right. So this concludes everything that I wanted to say, not just the proof. So we know how to compute isomorphism classes of abelian varieties up to isomorphism. We know how to describe them in terms of fractional ideals. And now we know also how to understand the polarization. All right, this is everything. Thank you very much for your attention.